So welcome everyone. So I'm going to discuss, as Colin's already said, how to prevent 80% of failures in 20 minutes, or maybe just over 20 minutes. So there's no need to take notes. As it's already been said, the content of this will be recorded and be on the BNDT website at the end. But you can also, if you want, and you go on to get some supplementary information, you can scan this QR code and you can download a series of books that go along with these types of topics on oil analysis if you just want to find out a little bit more. So who am I? So my name's Adam Cutler. I started the industry in 2011. I've previously been the business unit technical diagnostics manager for 7 years at two of Europe's largest condition monitoring labs before starting my own. I'm on the working group for LA analysis in BINT. Obviously been a fluid analysis trainer. Also do some work for IMECE as well on fluid analysis training. Consultant to BSI, various laboratory organizations. I run a YouTube channel, Learn All Analysis, and a blog on the topics all of oil analysis. Been featured in industry textbooks and publications. I also help peer review on the Insight magazine for BNDT as well, and also been on National Geographic Channel too. My contact details on the right. So again, if you want to reach out to me, if you've got any questions about oil analysis at the end of this, you've got my contact details and just add it straight to your phone if you scan this QR code. Again, I'll show this QR code at the end if you want to take it, if you haven't got a chance now. So 80% of failures, particularly in hydraulic systems, are caused by lubricant condition. The top causes are wrong viscosity of the lubricant, contamination with dirt, and contamination with water. And all of these are detectable before vibration, heat, or noise changes. So a lot of you may be familiar with the other condition monitoring technologies, such as vibration, thermography, acoustics, etc. And they all work on the principle that something's already going wrong in terms of wearing of the component, and then it starts detecting the fault occurring. These can occur before wear takes place. So the viscosity can be wrong, there can be a contaminant there, and this can all be detectable before you even see signs of wear. And so this is quite a good use case of oil analysis and how it complements a lot of the other CM technologies. In fact, when I've spoken to a lot of people and they say, when do you use oil analysis, particularly in like the vibration, I've spoken to a few people, and they say, well, I've got a problem with my vibration readings. I can't read what it means. So I send off an oil sample for a second opinion. But that's not really the right approach. You should be running them side by side, and then that information can be telling you something before you maybe even see a wrong vibration or a wrong thermography peak or acoustic signal in your samples. So this is why it's important. And again, 80% of failures are caused by these three topics in oil analysis. So if you can highlight these and get these, you a long way to getting a good reliability in your systems. So let's talk about the first of those, viscosity. So viscosity or resistance to flow is its definition. So an oil can be too thick. So when you have something that's too thick, it can give you high energy consumption, but low wear rate because you've got a big film thickness, a thick film thickness. Or it can be too thin, and so you're getting more metal to metal contact. So that metal to metal contact is leading to more wear occurrence, but you get better energy efficiency, at least at the start. Or you have it just right. So like the Goldilocks zone where you get the right balance between it being not too thick, not too thin, and you have it just right in terms of viscosity. Now, with a lot of modern formulations and how oils are designed, with energy efficiency being very key, it tends to be chosen to go right to that as thin as we can go, or as thin as we dare, so to speak, before it starts to cause wear. So you tend to find much thinner lubricants are trying to be applied in a lot of modern formulation lubricants. So how do we measure viscosity? So viscosity we measure it is actually a speed, so it's in millimeters squared per second, and we have something called a viscometer bath. So this is called a Julian bath, and we've got 4 tubes in here, and these are all soaking in. These are glass tubes, and these are all soaking in silicone oil, and we put a sample or a droplet of oil down the tube, and we time how long it takes to get from one end to the other. The thicker the oil, the longer it'll take to go through the tube. So if we do this now, we'll start with a thick oil and go to a thinner one, and we'll see how long they take. So I've just highlighted, we've got these 3 tubes of these 3 here. So let's put it down the tube. So going 1, 2, 3, and they're off. And we can see this 32 grade has got down before the 100 grade, and the one that started first is still going. And now that's finished because that's thicker oil, so it takes longer to go through. It's got a resistance to flowing, and this is flowing under gravity in these circumstances. So when we also talk about an oil, it's important to know the temperature that we're measuring it at. Because you'll notice when you've done your own cooking at home or anything like that, so you pour a bit of olive oil in a pan, you turn on the heat, and soon that's what seems quite thick oil that's in the pan is zipping around. It's gone very, very, very thin quite fast. And that's because that's got a low VI, so it's going thick. It's going from a thick product to a thin product very quickly with an increase in temperature. So if we were to take an engine, for instance, where the typical engine temperature may be, say, 90, 95 C, something like that, this is the operating temperature. This is what we care about because this is where maybe 90% of the time the engine is going to be running at. We want to make sure it's right at this point. And so we want this film thickness here to be correct. So we can achieve that. So we can achieve that, first of all, with this oil up here that's at 40 degrees Celsius is 140. But if we're getting it to like near to, we're coming into colder months now, as we're getting to like freezing or below, it gets thicker and thicker and it's going off screen in terms of viscosity. So that'll take a lot of energy to start up in the morning, or it's very, very thick and gooey. Or you can have an oil that just doesn't go as thin as fast. So rather than having the one that's up here, you can have the one that's over here. In the extrapolation of going backwards in temperature. Now, the way they achieve this is there is no perfect oil, first of all, that goes completely flat along here. There'll always be, and as you increase the temperature, the oil will get thinner. But they add additives to give the appearance of viscosity and increase it over time. So let's have a talk about the different ways and problems you get with viscosity. So I'm not going to go too much into the different viscosity classification systems, but I'll just cover the simplest one, ISO today, which is the main one for industrial lubricants. And so this is all measured at 40 degrees Celsius. And so you have a grading system. So you have an ISO VG or viscosity grade that stands for 32 or a 46 or a 68. And so if you've got a 32 at 40 degrees Celsius, it's 32 plus or minus 10%. At 46, at 40 degrees C, it's 46 plus or minus 10%. At 68, it's 68 plus or minus 10%. So if we're at 100, we know that if we've got a value between 90 and 110, that's plus or minus 10%. At 40 degrees Celsius, then it's an ISO VG 100. And so that's one of the classic ways of measuring the viscosity. So it's the main one we do in a lab, viscosity at 40 degrees Celsius. But viscosity can change, not so easy. We obviously know it changes with temperature, but between sample to sample as we're doing condition monitoring. And so there's a few causes you can have that. So you could have fuel contamination. So a fuel is much thinner than oil, and so that can reduce the viscosity. You can have water. Water is actually thinner than the oil itself, so that can reduce viscosity. You can have a wrong oil. So you may accidentally mix a 68 with 100. That's going to bring it down. You can have polymer shear. So these additives that are making it appear thicker than it is can actually be what's called sheared or broken down. And so they don't work as well as they did. And so you can, over time, see the viscosity of the product drop. And if you look at the reasons why the viscosity can go up over time, it's actually the same reasons. So when we talk about fuel, so fuel is thinner. But another thing that's also in producing an engine is soot. And soot can make the oil go thicker over time. If we talk about water, so water is thinner than oil, but if you mix them together, you get an emulsion or cream, which is thicker than oil. You can have a different oil, so you can have a wrong thicker oil. So if I mix a 220 with a 100, I'm going to have a viscosity closer to 150, for instance. And again, we've talked about polymer shear. So as an oil degrades, the additives degrade. Well, as the oil degrades, the oil is made up of different molecular weight compounds, and over time, the lighter parts of that start to volatilize off or boil off, And so over time, you get a thicker and thicker oil over time, and it sludges. So there's a few reasons why oils can degrade and oxidize there. So we've covered viscosity. We talked about dirt contamination, particularly particles. So one of the classic ways of measuring that, let's talk about scale first of all. So we've got a 30 centimeter ruler, took 1 centimeter, and then we're going to take that 1 centimeter and zoom in to 2 millimeters on that. We're going to zoom in again on that now. And we can see we've got 2 millimeters filling up the screen here. And we can see we've got a little image on here. It's just filling this small section of this 2 millimeter squared sample section. And we zoom in on that again. So now we're at a very, very fine scale. So just to put into context in size, this is a human hair. And it's a side-on. And if you watch shampoo commercials, you'll probably see these nice ones, and it'll be like a nice glossy split end being fixed in the videos. But this is across here, across the length is 80 microns, so 80 microns in size. So very, very tiny. And we're taking a section here of that 25 microns. So we're taking like a quarter of this here, and we're putting these little 3 dots on here, which are these 3 dots here. And just to put in perspective, this is a red blood cell. So they're very, very tiny particles here. And we're measuring 3 sizes, which is a 4 micron, a 6 micron, and a 14 micron. So this goes on to measuring what's called an ISO cleanliness code, which I'll come on to in a little bit. But just to put us back into perspective, here's a sand grain particle against the hair. So that's about 60 to 70 microns roughly in size. And then we've got this, it's just going off screen, putting it on the same scale as this 25 microns cross section here. So zoom out again. So as we can see, that's that picture we're just looking at on screen on a grain of sand, just to kind of scale it out for you. And you can see that there's a grain of sand there on my fingertip, 1 grain of sand on the fingertip. So we've been working on very, very tiny, tiny, tiny fractions of particles when we're talking about the sizes of these particles that can cause wear and problems in a system. Now, one thing I've forgotten to just say on this is I actually need to give a dedication on this one to my son, who kindly donated this grain of sand from his sandpit and said I did need to declare it in my presentation, that he'd given it to me. And I will return it after I finish this presentation, I can assure you. So again, talking about ways of measuring particles. So we have different ways of measuring them. So we can do elemental analysis. So this is perfect for very fine or dissolved particles such as additives, gives a breakdown of the elements present. The problem is that the max size, so these can only tend to work on 5 microns. So we had the 4, 6, and 14. So right at that bottom end is kind of the biggest particles that normal oil analysis can pick up. We can improve that with acid digestion, which if you look at any other presentations done for Bint, we talk a lot about that on Lubeware, what we do as a lab. You can also do laser particle counts. So this measures sizes 4 to 70 microns. So almost up to the width of a human hair here. Again, this is size only, so it gives no elemental shape or breakdown of the shape information. We can do it gravimetric, so we can weigh the amount of particles there. But again, this doesn't give any distribution of the sizes within that weight there. We can do it by microscopy, so we can look at the shape and size of those, but it doesn't really give you anything about the elemental data on it. And equally, something you can do, it's completely free. You can just look at the sample, so you can visually inspect the samples too. The limitation on that is generally you don't get anything beneath 40 microns you tend to be able to see on that, depending on your eyesight. So on here, this is called a laser particle counter. So I'm just going to rewind this one slide here before I go ahead. So we're going to pass, and the way this works to measure the cleanliness of the oil is we put oil through a tube and we shine laser beams from one end to the other. And as we shine it from one end to the other, we are looking for particles flowing past, and as they block, they cast a shadow. And so we're measuring effectively the shadows or the light, what's called light obscuration, as it passes from one side, from the laser beam from one side to the other to give a detector. So I'm just going to rewind one slide and I'll just go back to that. So we'll watch this slide here to present that for you, how that's working now. So we're shining a laser beam across and we're having the particles. And so it's had a few 4 microns or a 6 one now, 6, so a big one, a 14 in there, a few going across, a bit more 4s, one big 14, it's moving across. So at the end, we get a count generally per mil. So I've got 8,271 particles at 4 microns, 1,622 particles at 6 microns, and 193 at 14 microns. Now, if I asked you just to repeat that back to me without looking at the screen, you'd probably struggle. But if I said, can you just say to me 20, 18, 15, repeat that back to me, you'd probably quite easily say that. And so this is what the ISO cleanliness code is designed to do. It's designed to make these numbers that are too big much, much easier to work with. And so let me just explain how the coding system works. So we normally quote it in per mil, per millimeter, but most easiest way to describe it is per 100 mil, which generally, if you're working in an oil lab, they'll use like a 100 mil oil sample bottle. So if you think per bottle, if you've got 1 to 2 particles, we give it a code of 1. If we've got 2 to 4, we give it a code of 2. 4 to 8, we give it a code of 3. 8 to 16, 4, etc. So each time we're doubling the amount of particles, we increase one code. So if we have a look at this here, so this is the 4 micron, this is the 6 micron, this is the 14 micron count. As we go from a 4 to a 6 to a 14, if we go up a code, that's 21, 19, 16, that's twice as dirty. If we go down a code, so 19, 17, 14, that's twice as clean. If we go down 2 codes, so we went down to 18, 16, 13, that is, it's half the dirtiness, then half again, so it's 1/4 the dirtiness of the previous sample. So let's put these codes in perspective. So a typical new hydraulic oil would have a cleanliness code of 20, 18, 15, which is actually quite dirty because most manufacturers will specify they want it to be 18, 16, 13, which is 2 codes, so 4 times cleaner than this, as their maximum amount of dirt they want in it. So the only way you can actually achieve the targets is to start filtering straight away because you need the filtration to get it to the cleanliness is required for the manufacturers. And this is why contamination tends to be one of the big issues because they design them for a much cleaner environment that you can physically work with a lot of the time. If you work with a lot of other systems, you work in aviation, you may come across called the NAS system or SA4059. So this works a very similar system, coding system. But what this works on, it works on the worst case scenario. So you can imagine aviation, you work on the very worst case scenario in all of these. And so they say, okay, we get a cleanliness code and it goes all the way up to 12 from treble 0 to 12. And we say, okay, on the 4 micron, we had this code, it's an 11 because it's the worst one. And as you can imagine, you could have like a million particles here, but just 512 of the greater than 70 microns count would give you the same. And this is per 100 mil, not per mil on these. So these are 100 times more stricter than you would see on your standard particle counting measurements. So you can also do oil poured through a filter paper. So you can do what's called a patch. And so you can visually inspect them. So you can see here, this is a patch which got a 14, 12, 8 count. And this one here is a 23, 21, 19. So we can see we've gone, in this case here, we've just gone from 12 to 18. That's a 6 code. So that's 2, 4, 8, 16, 32, 64 times dirtier on this, and you can see here. Then we can do it by weight. So we don't have to measure it by inspecting it. We can do it by filter patch. So if we take a filter patch, we go and weigh the patch first of all, get a weight for it. Then we go and pass through under vacuum the sample and we capture the debris. You can see the debris collecting on here as we're collecting it. Then we can go and weigh it again. And then effectively weigh the difference with just a few calculations. So I'll just let those calculations load on screen for you there. Okay, so you can see we've got milligrams per kilogram, 3.79 milligrams per kilogram, or 37 milligrams per kilogram when you multiply it up to the scale of what you put through. You can also visually inspect the sample. So this is looking at the bottom of a sample. So you pick a bottle up and then look underneath at it. And you can notice on our bottles, we have a domed base. So all the material collects around the side. So you can see here, so this is like one that's got 10 milligrams per kilogram, 100, 250. You can see it's 1,000 milligram per kilogram one is pretty dirty here. And one thing you can see is with particle count, the significance. So you can actually extend component life significantly. So if we were to say that we started off on something that was originally 2018-16, and we managed to get it to say, so we got it from 2018-16, managed to get it to 16-14-12 as target, we could actually improve the life of the component by 3 times. So you could get a 3 times that component life purely on reducing contamination. So a little bit of microscopy analysis as well. That's another way of assessing particles and seeing what's in there. So one of the things for a lot of people is that a lot of them will go and look at SEM microscopes or SEM microscopy. And the reason is you get some nice pictures. Apologies for anyone who's squeamish here. But you can see you get some really nice pictures by electron microscopy. You can see this fly's eye, if you can see here. Point is that light microscopy is pretty good too. And in fact, this image is light microscopy here. So if we just talk a little bit about where materials are formed, so we have what's called a shear mix layer, which is formed as you get the initial asperities, so the contacting surfaces, break off and they react with additives, form a boundary lubrication additive layer on the top, on the surface, which when those two contact, that's what we get. This is the boundary lubrications contacting, and we get normal wear. When that's overwhelmed, we get metal to metal contact, which is sliding wear. So this is sliding wear. This is a sliding wear particle here. And you can see it's almost got like a grain. So if you've got like a nice wood grain, you can see like almost like a grain to the particle going across in sliding wear there. You can also have, these are some crystalline particles, look like sand here. And these are important because when we're talking about dirt, its size does count in this case. So a small particle, smaller than the tolerances of the machinery, goes straight through. A big one can't get into the gaps of the surface, but one that's just the right size can get it trapped between and gouge out surfaces of the material. And you get these long, thin particles, which look like you've obviously had a potato peeler on the system, and you can see you've got like a long gouged out piece of metal here. You can also have on a rolling surface, so you can get fatigue wear. So on here, we've got equivalent to 10 cars on your fingernail pressure, and this turns the oil physically solid at this point here. And we're effectively, as the rotating surfaces, the vibration, any vibration people will notice is happening, you actually work hardening the surface. So you're effectively hammering that droplet of oil, which is actually solid, into the surface, and you form a little pit over time, which can then develop the wear materials form little spalls, and then dirt can get into that gap. And then as that comes in, you can then chisel out a fatigue chunk. And so what you get initially is what looks like little ball bearings, but actually these are spalling wear, so early signs of fatigue wear. Then this can eventually turn into fatigue wear. So fatigue wear is classically described as looking like orange peel, although I think it looks more like a child's drawn a little island picture on this. Again, you can get other things like fibers and rust flakes you can see in samples. And again, sorry for the squeamish people, again, little insect legs. Unfortunately, this was actually in a food production facility's oil samples, which doesn't make you kind of fancy their foods at the moment, quite honestly. This is an interesting one. This is called laminar wear. So the particle actually broken off. It started off as a fatigue chunk, and then it's gone through and been rolled over. So it's actually gone back through the system after breaking off and been rolled in the opposite direction, as you can see that here. So we've covered viscosity, we've covered dirt and particulates. The next thing to cover is water. So water degrades lubricants to form acids, promotes oxidation, promotes rust, forms emulsions, which are themselves are poor lubricants. It hydrolyzes or breaks down the oil additives, and it washes out any detergents, so keeping all the dirt and contamination from depositing on system surfaces. So water in a system is not very good. And the easiest way to do it is what's called a crackle test. Hopefully you can hear this when it comes up. And so the classic things that will cause this are things like coolant leaks in an engine, porous liners, gasket damage, poor maintenance practices is quite common, so poor lubricant storage conditions as well. So just to recap, 80% of failures in hydraulic systems and the other types of systems such as engines, gearboxes, compressors, are not that far behind, are caused by the lubricant condition, and they're all detectable with oil analysis. And these are all detectable very, very early, even before you get onto the stage of wear and the other CM technologies detecting a fault occurring. So congratulations for making it through this approximately 20-minute presentation. I'm actually tying myself I'm a couple of minutes over, but hopefully you don't mind too much in that. But I've got a little treat for you at the end here. So obviously you have listened to me quite patiently. And I think that both you and I also think any oil sample should deserve a break. So I'm just going to put that something on screen for you guys now.
Welcome to North Wales, home to oil analysis laboratories. Wales is famous for its diverse wildlife and its great weather. But at Oil Analysis Labs Resort, the weather is hotter. No much hotter, not quite hotter still, that's right. At our lab, the weather in the ICP, inductively coupled plasma, is a toasty 10,000 degrees Celsius, twice the surface temperature of the sun. So, pack your sunglasses, because we're testing your samples in style. But where are my manners? I'm already vaporizing your samples and haven't even checked they've arrived safely. Thankfully, our express courier service whisks your samples from their machinery home to our lab, where they get the red carpet treatment with a personalized photo shoot on arrival. Ready for your close-up? After the glamour, it's time for some analysis. Your samples get a microscope inspection before some fun and entertainment on the Ferris wheel, where they take a spin in our magnetic field to check for metallic debris. Next up is the relaxation phase, our calming massage rollers, where your samples mellow out and mix with new friends before subsampling for testing. And don't worry about refreshments. At Oil Analysis Laboratories, our automatic sample diluter ensures your test tubes are always topped up. Feeling adventurous? Your samples can take a plunge on our warm 40 degrees Celsius, the water slide. Watch them race to the bottom. Will they be ISO 32, 46, or 68? Their time to the finish will tell. It's so popular, everyone wants a turn on our automatic viscometer, because viscosity is, after all, the most important property of an oil. And don't worry, there are plenty of tubes for everyone to get a turn. While you wait, why not detox in our distillation sauna? Vapors reach nearly 400 degrees Celsius to separate things out. Too hot? No problem. Chill out in our cloud, pour and cold filter plugging point instrument at an icy -40 degrees Celsius. But watch out for those wax crystals. Feeling active? Burn calories in our bomb calorimeter, test your endurance with the rotating pressure vessel oxidation test, or pump some iron with our 4-ball weld test. At Oil Analysis Laboratories, your samples get the VIP treatment every step of the way.
So thank you very much. Again, I've put on the QR code to scan so you can get copies of all the handouts. And again, obviously reach out to me if you've got any questions on this as well. Okay, thank you very much. I'll hand you back to Colin now to just finish up.